Good morning, myself Sheikh Shoaib Akhtar from Mechanical Department. Today my topic is CFD flow analysis challenges, navigating complexity in fluids simulations, why CFD matters and it's too why it's tough. CFD enhance CFD enables virtual prototyping, saving millions in costly physical testing, yet it remains freakishly complex, requiring deep expertise, powerful computing resource, and meticulous validation. A common misconception suggests CFD is merely colorful fluid drawings, but the reality is far more nuanced challenging. Virtual prototyping elements expansive physical test, technical depth, demands experimental rigor, validation, critical results must be verified against experiment. Challenge one: meshing complexity and grid independence. Industrial geometrical turbines, pumps, heats exchanger, and or irrigate making mesh generation extraordinarily time consuming. Poor mesh quality, skewed cells, insufficient resolutions near walls causes inaccurate results and convergence failures. Engineering constantly struggle balance mesh density against complex cost, a trade off that directly impacts solutions quality. Geometry complexity in intricate industrial shapes and demand hours of mesh preparation. High quality versus cost. High mesh density improves accuracy but increase competition burden. Grid independence. Iterative refinement required to ensure solution independence. Challenge 2: Turbulence modeling and physical accuracy. Turbulence remains the holy grail of CFD. No universal model suits all flows regimes. Selecting appropriate models, RANs, LEEs, DNS directly impacts both accuracy and computation demands. Missing critical physics compressibility affect multi-phase interaction, heat transfer, coupling, introducing systematic errors that undermine prediction reliability across diverse engineering applications. Model selection dilemma. Each turbulent model runs least uh, DNS offers trade offs between fidelity and caste. Physics gaps. Ignoring ignoring compressibility, multi-phase flow, or thermal effects cause flared prediction. Universal lamination. No single turbulence model accurately predicts all allow all flow conditions. Capturing turbulence, the unsolved puzzles. Understanding the predict turbulent flows remain one of engineering greatest unsolved challenges. These visualizations illustrate the Charcot multi-scale vortex structures inherent in turbulent motion. Capturing this requires extraordinary complexion resource and sophisticated modeling approaches. The complexity of turbulence demands continuous invention in both computational methods and theoretical understanding. Challenge 3: Computational resource and simulations time. High fidelity simulation demand HPC clusters or expensive cloud computing, often unavailable. Small engineering frames, larger transmit or multi-physics problems rotatingly require days or weeks to converge industry time to pressure force engineers to simplify models directly risk solutions accuracy and design confidence. HPC access limited availability in smaller organization simulation time days to week for complexity transmitment problems accuracy trade-off time pressure drives model simplification risk cost modern cloud computing expensive accelerated rapidly. Challenge for numerical stability and convergence issues. Improve boundary condition expensively large time stress tests or probably configured slower settings triggered divergence or unphysical oscillation residual monitoring and convergence threaten are technically brutal yet frequently misunderstood or overlooked by precision high back pressure zones strong regulations visions and boundaries layer phenomena routable causes simulations collapse without medically exploiting and problem identification poor boundary condition in incorrect domain setup. Second, solve configuration in inappropriate time steps and slower parameters. Convergence monitoring, judicial and physical fluid checks required. Expectoral interaction turning needed for challenging flow regression. Challenge 5. Challenge 5 validation and uncertain quantification. CDFC result must be rigorously validated against experiment or field measurements, a costly time confusing indie or uncertain areas from mesh resolutions, turbulence model selection, and boundary condition assumptions without systematic validation and uncertainty characteristics CFD predictions risk reliability, practically in safety, critical aerospace, automotive, and defense applications. Source of uncertainty, mesh size effects, turbulence, model choice, boundaries, conditions, materials, properties. Validation requirements, experimental data, filed measurements, rigors, compression, errors, quantification. Challenge 6 communications and interpretation miscommunication between CFD analysis the design engineering teams frequently results in incorrect boundaries condition or mismatch of result insufficient physical understanding in place flaved estimation and poor model setup transparency in CFD workflow documentation and clear communication remains persistently industry challenges limiting knowledge transfer and reproductively across projects. Analysis designers gap boundary conditions often misspelled due to unclear communication. Physical instead missing lack of domain knowledge leads to poor model expression. Documentation defensive CFD workflow rarely documented competently for reproducibility. Reproducibility. Result miniaturization non specialists often mistreat visualization and matrix. Emerging foretells the road ahead. NASA 2023 CFD version identifies the grand challenges wall resolve large additive simulation of industry transmitter turbofan simulation multidisciplinary optimization and probabilistic uncertainty analysis artificial art, artificial artificial intelligence and machine learning promises accelerated uncertain faster simulation continuous cross disciplinary collaboration and methodologically innovation remains systematic overcoming CFDs ensuring technicals during advanced modeling wall resolved less LES of for industrial accuracy AI integration machine learning accelerator uncertainty analysis multidisciplinary design coupled optimization across disciplines, collaborative collaborative excellence, knowledge sharing, and continuous adva- ad- advancement. Thank you.